Okay, this is going to be the Calculus 3 lesson video for 13.3, the first part where we're going to talk about arc length. So let me go ahead and present the notes. All right. So for this first, to try to connect to things that we've seen before, and back in AP Calc BC or Calc 1 or Calc 2, probably Calc 2, whenever we talked about this chapter might not be meaningful. But we said that if we have a regular function, y is a function of x, and there's a curve, function curve, and we wanted to find the length of the arc between 2 points on that, we could approximate that length by dividing it up into small little line segments here. And the distance between any line segment pair would be the square root of the difference in the x squared plus the difference in the y squared. Right, so a delta x squared plus a delta y squared square root, that gives us the distance formula. And then we're doing something to add up all those lengths. So we will add up potentially an infinite number of these things where the number of line segments approaches infinity to try to get this as smooth as possible. And then by the mean value theorem, the derivative of the function at any particular x is the change in y over the change in x for an infinitesimally small x and y. So you could approximate the change in y by taking the derivative at that x value times the change in x, right? And so if I took this expression and used it in place of this right here, I would get this structure, right? And then if I factored out the delta x squared on the side here, then that would leave 1 plus the derivative function squared at particular x's, right? And so this just becomes delta x. And so essentially what we're doing is, to try to do this smoothly, we're doing an integral, and we're integrating along values of x. So with respect to x, we're integrating, right? And in order to get the arc length, we have to have something that adds up the individual little pieces of arc length, right? And so the expression that we derived is, the expression that is the arc length is the square root of 1 plus dy dx squared. If you integrate that structure, 1 plus the square root of 1 plus dy dx squared, you're going to add up all these little individual arc lengths. Okay, we're integrating it over the x variable. So the first time we encountered arc length in AP Calc BC, it was like this, right? With respect to the input variable, right? And then later in the course in AP Calc BC, when you talked about parametric equations, it was chapter 10 in the Stewart book. You could represent a function y and x, where y and x are both functions of this new parameter t. So x is a function of t, y is a function of t, and now we have something like what we're talking about now, where we have, integrating from the parameter t equals a to the point where the parameter t equals b, and adding up those things. So starting with that thing we did before, where we would integrate, from x1 to x2 with respect to x. If you do some manipulation here, like you multiply top and bottom here, divide top and bottom here by dt, and multiply this by dt over dt, then you can slide this dt over here and get dx dt, right? And then if you were to say, okay, I want to get it so that I can put it inside the radical, I can take the square root of that squared, and then take this dx dt squared and multiply that into here. So you would get this integrand, the square root of dx dt squared plus dy dt squared, and this time integrating with respect to t. So what happened here is that we have a new expression for the little arc length here, right? And that arc length is now, we're summing over t. So instead of summing with respect to this, we're summing with respect to the t parameter. So that's the second time we saw arc length, back in AP Calc BC. And we had using an integral to sum up pieces, right? This time with respect to the parameter instead of with respect to the input variable. Okay, so now we have to extend all this to our vector function space, which essentially just means we have to add on a z, because when we represent r as a vector function where we have x of t and y of t and z of t, right? We already are doing something very much like what we did before. We just have to add on a z, right? So in fact, that's what we're going to do to define arc length now. We're going to say, okay, we have a third dimension, so we still have parameters going from a to b, okay? And so I'm just going to take that Calc BC expression and just add on a plus square root of dz dt squared, right? So this is an expression that can be used. It's in our textbook for that, but we actually know something else. We know that the tangent vector, not the unit tangent vector, but the non-normalized tangent vector with its length, actually is the derivative of x in the x direction, the derivative of y in the y direction, the derivative of z. And if we were to take the magnitude of that vector, it would be exactly this term right here. So what we're going to use in this class for finding arc length is, you can think of the tangent vector as being a little vector, like these little blue vectors that are in the direction of the curve, right? And if we sum them up by taking an integral with respect to the parameter t, moving in from some starting t to some ending t, adding up all those magnitudes of the tangent vector produces the arc length, which we'll call L. Right, so that's our first and main way to compute arc length. It's just an extension, really, of what we've done in AP Calc BC. But now that we have this tangent vector definition, we can write it in a more compact form than we would have had to from before. Okay, so that's the first thing. Let's do a quick example. Let's say that we wanted to find the length of the arc of the circular helix with the vector equation that R, the position vector, is cosine t in the x direction, sine t in the y direction, t in the z direction. So it's a counterclockwise spiraling helix. And we want to go from the point 1, 0, 0 on that helix around this blue curve and stop at this location here. So we want the length of this curve in 3D space. Now at this point, we're back to 1 for x and 0 for y, but now t went from the z, which is also the t, went from being 0 to pi over 2 to 2 pi. All right, so what we're going to say is we're going to say that the length, the arc length, is equal to an integral of, and we have to take the magnitude of the tangent vector and then integrate that over t from some starting t to some ending t. Okay, so we have to figure out what values to use for the limits of integration. So since our initial vector is defined with t as the z variable, we're just going to start, that means that this 0 means actually also t is 0 at this location, and this means t is 2 pi. So we would be integrating from 0 to 2 pi. And then all I need is an expression for the magnitude of the tangent vector. So we know that the tangent vector we find by taking the derivative. So we take the derivative of cosine to get negative sine, and the derivative of sine to get cosine, and the derivative of t is 1. And then we can take the magnitude of that. Now that's going to be the square root of negative sine t squared, right, which is sine squared of t, and then cosine of t squared, which is cosine squared of t, right? But by the Pythagorean identity, sine squared plus cosine squared is actually equal to 1. So all of this is equal to 1. So 1 plus 1, it's just the square root of 2. So what we have to integrate, so we're just doing the integral from 0 to 2 pi of, this is just the square root of 2 dt. And so using the fundamental theorem method, we just take the antiderivative, variable is t, we evaluate from 0 to 2 pi. So you plug the 2 pi in here, and then you plug the 0 in here, and that computes to 2 square root of 2 pi. So that is the numerical length of this blue arc length along that space curve from a given point to a given point. Okay, not too bad, as long as we can come up with reasonable derivatives here. And I mean, this could be either fairly simple like this, or it could be really, really hard, depending on how the integrals are. But one thing about this class is, since we're already done with AP Calc BC, Calc 1, Calc 2, this class isn't really about the integral. So when integrals get really hard and nasty, we'll either look things up in the table in the back of the book, or we will just go ahead and do the setup, and the setup will be the answer. And we can use a calculator to check it if it's a single integral. All right, so a couple other things to add on before we wrap up for arc length. The first is that now that we have a way to calculate the length of the arc, we could write that arc length as a function of the parameter t. So it might be nice if we could say, okay, let's have a function s, which is the amount of arc along the space curve for a given value of t. Okay, so for example, I'm going to switch notations now. So instead of using t for the parameter, it kind of still is, but let me switch to using a u for a second, like a substitution. So if I were to say r prime of u, where u is the parameter, Okay, so first I would start at some known position, a constant like a, and then I would go some arbitrary distance along the space curve until my parameter u is at a variable t. And that gives me my first position vector is the position vector RA, and this would be R at the generic value t, where t can slide around. Right? What we're saying is if you were to then take the integral of this structure from a to t for the u variable, right, that would essentially give me the length of the arc from a starting known location to an arbitrary t value. And that allows me to express this blue arc length, as a function of where we decide to stop. Okay, so we have arc length as a function of t. All right, so by the fundamental theorem of calculus, right, we know that whenever you have something that's from a constant to an x, especially 0 to an x, then that means the derivative of this side is equal to this function, right? And so if we were to take the derivative of both of these sides of this expression, that means that that the derivative of the arc length function would be just equal to the magnitude of the tangent vector, right? And another way to kind of remember what's going on is you can just say this: the magnitude of the tangent vector represents the rate of change of the arc length as we move along the curve. And in fact, we can find a function for this arc length by just computing this and then taking an antiderivative with a variable. Okay, we'll see examples of that in the homework, and we'll talk about that more fully when we get to that. But there's another kind of concept we have to talk about today, and that is that we can parametrize the curve with respect to its arc length. So let me go back to the beginning of the lesson here and show something. So when we talked about this stuff before, when we had this version of this formula, we were integrating with respect to x. So we were integrating with respect to the input variable in the domain, right? And we had to have some expression for arc length for that. And then later in AP Calc BC, we had a different expression when we wanted to integrate as I varied the t parameter. So not with respect to the spatial variables, but with respect to the parameter variable, okay? And those are two different things, and we have to have a different expression if we change from input variables to from spatial variables to the parameter input variable. So we're going to kind of do the same thing here in 3 dimensions, okay? We can use the derivative expression to change the parameter to be a parameter of the arc length. So right now, right, when we do the integral, let me go back to this thing let me go back to the one we did. Okay, so when we did this integral, let me use a different color here, right? We were integrating with respect to t. And that means that we're integrating up little pieces here that are with respect to as t is changing, right? Okay, but t is not necessarily changing in an even way as we go along the parameter. Instead, we could say, well, what if I figured out the length and divided up this length into, so instead of like that, maybe I could say, as we go along t, these t's might vary. Like if I go from t equals 0 to 1 to 2, that doesn't necessarily go an equal distance along here. But this is an integration as we steadily move through t. But what if we wanted to instead change the parameterization so that it was in terms of little units that were equally distant along the arc length like this? Then that would be parametrizing versus distance along the arc instead of distance along the input parameter. Kind of like in the beginning of the thing, we went distance in the parameter instead of distance in the x. Right, so to do that, we would have to what we call reparametrize the curve, but this time with respect to distance along the arc. Okay, so this is how we would do that. Okay, we're going to start with the magnitude. So let's say we have this helix that we said the position vector is cosine t sine t, and we want to reparametrize this for the same distance here, but with respect to the arc length instead of with respect to the parameter t. So if we start with the magnitude of the tangent vector, right, which let's actually just do that again. So we know that the tangent vector it would be the derivative. So if I did the derivative vector, that's going to be negative sine t cosine t 1, okay? And then if I take the magnitude of that vector, I'm going to get the square root of the sum of the squares. So this is going to end up being sine squared plus cosine squared plus 1 squared. everything is weirding out here. But sine squared plus cosine squared is 1, so this is the square root of 2. So we did that before. So what we're going to do now is we're going to say, okay, there is an arc length function s such that the derivative of that function is equal to the magnitude of the tangent vector. And then to find this vector, I'm going to just take the integral of both sides with respect to t. Yeah. So let's say, okay, let's take the integral of both sides with respect to t. Okay. And this would then be taking the integral with respect to s, taking the integral of the square root of 2 with respect to t. This would be like taking the antiderivative of 1, where s is the variable, and this would be the square root of 2 times t. Right? And so this allows us to now relate t and s, where this is distance in t, and this is the corresponding distance in s along the curve. I wish my thing would cooperate. Okay, so what that means is you can solve this for t and get that it's s over the square root of 2. And then everywhere you see a t, you can replace s over square root of 2. So when I had my original r as a function of the parameter t, cosine t, sine t, t, I can rewrite this now as a function of the distance along the curve, s. So it'd be cosine of s over square root of 2, sine of s over square root of 2, and z would be s over square root of 2. So doing this is referred to as reparametrizing with respect to the arc length s. Okay, tricky. And I think we're in a position now where a lot of these things are hard to kind of completely wrap our minds around what's happening. But the reason we would do this is we could now use the arc length computation. We could do arc length, but use the reparametrized curve. So if I wanted to do that, I could say, well, my function r is that, right? I just did that on the last idea. And so I'm going to have to take an integral, but this time I want to take an integral for the arc length with respect to s, okay? Not t. I want to go along the curve rather than along the values of t. So that means, first of all, I need to figure out what the endpoints are, right? We know that this endpoint is t equals 0, right? But I also know that s over square root of 2 is equal to t is 0. And that means that, in fact, s would also be 0 there. This location, we said, was t equals 2 pi. But t is s over the square root of 2, so that's equal to 2 pi. And that means s would be 2 times the square root of 2 times pi. So when we integrate, we're going to integrate from 0 to 2 square root of 2 times pi. And we have to use the magnitude expression, except for the magnitude expression for r as a function of s, right? But here's the beauty of this. Right? If you carefully took r prime of t and you substituted s over square root of t in there, right, and carefully went through all this, you're going to find out that it always equals 1, right? Because we specifically parametrized it per unit. So that means we don't have to have this more complicated we don't have to use this. Let me go back. We don't have to use this expression. When we do have to use this when we're integrating with respect to t, but when we're integrating with respect to arc length, we just get to integrate 1. So it's just going to be 1, and so that would be the variable s from 0 to 2 square root of 2 pi, and we end up getting the same 2 square root of 2 pi that we got before. So in my mind, it's kind of 6 in one, half a dozen of the other, right? I mean, you're either going to do a bunch of work to come up with this value, and then integrate over easy to find parameters, or you're going to have to do some complicated reparametrization in order to end up with this being 1. And so the work is, you're going to do the work either way, but the book does talk about both methods, so I thought we should talk about both of those. All right. So that's where we're going to stop, because that is more than enough to try to wrap ourselves around before we start talking about curvature. So we'll leave curvature for the second part video.